In 1905, on his way home from work, Albert Einstein was riding a tram and could see the Zeitgeist clock tower and its hands ticking. He imagined what would happen if the tram were to travel at the speed of light, and using just his imagination deduced that the hands of the clock would freeze, and came to the conclusion that the faster you move through space, the slower you move through time. This led to the later discovery that space, which we're used to thinking of being 3D, is actually combined with time into a four-dimensional concept called space-time. To understand this concept, we have to look back at gravity. Newton described gravity as a force that pulls objects with mass together. However, Einstein said that gravity changes the shape of the space-time fabric around an object. Therefore, any object with mass bends space-time around it. Picture a heavy object on a sheet or a trampoline. An object that's bending space-time is effectively bending time itself. So, time runs slower where there is more gravity. Or if you look at it in another way, where there is a larger bend in space-time. This is called gravitational time dilation. It's important to note that the closer you are to the center of the Earth, the deeper into the bend of space-time you are, which is where time runs slowest. In 1971, Joseph C. Haffel and Richard E. Keating came up with an ingenious method to test this theory using extremely accurate atomic clocks on airplanes. One clock was placed aboard a plane that flew around the world twice. The other was left at ground level. When the plane returned, the times on the clocks were compared. The clock that had been aboard the plane was slightly ahead of the one that was left on the ground. Obviously, the difference was tiny. For example, if the clock was set 9 kilometers above sea level when Earth formed about 4.6 billion years ago, today it would only be about 39 hours ahead. And of course, there's an equation for this phenomenon. Let's take a look at it. First of all, T0, which is the proper time. This is the time recorded when the observer and the event are at the same point in space-time. Next, there is TF. TF is the time as measured where there is no gravity. The G is the universal gravitational constant, which is this. And R is the distance from the center, or just the radius, of the object whose gravitational force the observer is experiencing. M is the mass of that object. C is the speed of light. There are two main variables in this equation, the mass and the radius of the object. If you increase the mass and decrease the radius, two factors that would increase the gravitational force on the observer, time decreases. Gravitational time dilation has got to be one of the strangest revelations in Einstein's theories of relativity. Time has always been seen as a steady constant, but in reality it can be warped. However, no theory is set in stone, so who knows what other constants may actually be variables.